Hello again, grade 10s. We are going to start looking a little bit at using exponential functions to model things growing, things decaying or getting smaller, and it's something that it's a way that we can use exponential functions quite a lot. In particular, it's used to represent how things grow, whether those are something like a bacteria growing or the population of animals growing, and also things getting smaller. So when radioactive material decays, it follows an exponential function. The third area that exponential functions can be used a lot for modelling are when we're looking at things changing due to either appreciating, so getting more valuable, or depreciating, so getting less valuable. So it could be that we're talking about an investment, or we're talking about the value of some sort of item. What we'll find is that we might need a little bit more than just a very simple function. So a function like 2 to the power of x is quite simple. We might need to do some transformations. When we started working on the Desmos activity, with the marble slide one, we were starting to learn about transforming these. So we sometimes transform them by adding a number on the end, or even adding a number in the exponent. We can also transform them by multiplying. So adding translated our function. It moved it left or right, or it moved it up and down. When we multiply, so let's have some examples where we multiply. Let's say we start with 3 to the power of x. Let's put some multipliers in different colours. I could multiply it by 100, for example. And I could multiply the power by, negative 0.1. And what this is going to do is it's going to cause the function to stretch. Putting in a multiplier here will cause it to stretch vertically. Putting in a multiplier in the power will cause it to stretch horizontally. And this just helps us to really fit an exponential function to the object that we're trying to model. So in general, we might have something that we're multiplying in front of our exponential function or even inside. Let's take a look at an example together. So this example should be on the next page of your booklet. We've got a breeding program to ensure the survival of mongooses. It was established with an initial population of 40 animals, so 20 pairs. From a previous program, the expected population, p with a subscript of n, in n years' time is given by this function. So let's just take a look at the variables we've got. We've got p, n, and n. N is time. Time in years. Pn is the expected population after n years. And let's take a look at the function. It says Pn is equal to P0 times 2 to the power of 0.2n. So what is P0? P0 looks a little bit like this Pn. So all we've done is changed n, the number of years, to a 0. So P0 is the population after 0 years. So if it's after 0 years, it means it's the population at the start. The word we might use for that is the initial population. Okay, we could have P2 or P5 to be the population after 2 years or 5 years. So this is our function then. To find the population after however many years we want, we take the initial population, which we were told, we times it by 2 to the power of 0.2 times the number of years. So let's take a look at these questions. Part A, what is the value of P0? Well, we said that that's the initial population, and we're told that the initial population is 40. What's the expected population after 3 years? All I'm going to do is I'm going to substitute in 3 for n. So P0 is 40 times 2 to the power of 0.2 times n is 3. I'm going to put this into my calculator. Let's just do this quickly now so that you can also check that you're getting the same answers. 40 times 2 to the power of 0.2 times 3. And I get 60.628 ... So we could say 60.6, but really if we're talking about the population of an animal, it might be a bit more sensible to round it. You could argue that you need to round up to 61, or you could argue that we haven't quite reached 61 yet and 60 would be more appropriate. Both of those answers would be acceptable. It's the same idea with part 2. We're going to have 10 years, and part 3 we're going to have 30 years. We will take a little look at sketching the graph. Let me just get rid of some of this. Make a bit of space for us. Okay, let's have a quick sketch of the graph. Okay, what you can do, if you're not completely sure about what the graph will look like, obviously you can type the function into your calculator. 40 times 2 to the power of 0.2x, and take a look at how your calculator sketches this. Okay, we'll see that it seems to have an asymptote around the x-axis, so I haven't gone through the x-axis. It doesn't cross the y-axis at 1 because of this stretch. It crosses it at 40. That's what we found out in part A. Now, thinking about my sketch, does it make sense? I've got this section here, which is all negative time. That doesn't make sense. So let's have another go at this. What I really want are axes that don't concern themselves that much with negative time. So here we go. Instead, it will look something like this. I'm going to mark on the point I know, which was 40. This is my population, and this is time, and that would be a sketch. I could also add in my answers from part B. So from memory, 3 was about 60, I think. So I could write it as a coordinate. 3, 60.6, and then I could mark on 10 and 30, and I could add them as little points along there. Finally, use technology to graph this. Well, we've already done that. To find out how many years it takes for the population to reach 400. So I want to see, when is my line going to reach 400? So this is what I want to find. When this is 400, what is the answer in years? How can I use my calculator to do that? Well, I've kind of drawn on what I want. I want to find this. I need this line, so I'm going to add in a second function. I'm going to put function 2 is equal to 400, and it will draw that red line on for me. I've got to scroll a little bit up on my calculator, but they do intersect, and then I can use function intersection to get that point of intersection. It happens at 16.6096. That is this point. So how many years does it take for the population to reach 100? We could say it takes 16.6 years. If we were trying to give our answer in whole numbers, we would have to round up. After 16 years, we're going to be a little bit further down our curve. We won't have reached 400. We'll be at 300 and something, I guess. So it's going to be roughly 17 years if we wanted a whole number answer. Okay, please have a go at the other 2 questions below the page. There is a worksheet on It's Learning for you to have a go at homework. If there are any questions, please save them. We can talk about them next week. Good luck. Bye-bye.